Hi, this is my first lecture with you all. Alright, mth3101, right, 3101 Advanced Calculus. So I will take over the class from Dr. Amir, yeah, and then from now on till the end of the semester, you will be with me. And for your info, this is the way I give my lecture, where I do a pre-recorded video and then I upload it to, and then I upload into the YouTube, and then I give link in the Putra Blast, right? Alright, so in the first lecture here, I will cover chapter 4, where we deal with a double integral, which include double integral over rectangular region, over more general region, include the Riemann sum and iterated integral, and any related to the double integral, right? As well as double integral in polar coordinate and so on and so forth. Alright, so let us begin our first lecture. I will describe what we mean by Riemann sum and so on and so forth, and then why do we call the region that the integral give the area under the curve and so on and so forth. Okay, alright, first let's start with some review on the definite integral. Yeah, we review on the definite integral. It's not that clear, I don't know why. Alright, so that's better. Review on definite integral. Alright, for the function, let's say if a function fx, or I can say y equal to fx, is defined on the interval AB. Alright, so what do we do is that if, let's say we have the function, this is our function y fx, yeah, well defined function, and between interval A and B. So what we do is that we split this into sub-interval, many sub-interval, n sub-interval, let's say. And then for the n sub-interval, we have, let's say here is we have xi minus 1, and that point there is xi. So we can see we have x naught, yeah. Here we have x naught until xn minus 1, or you can start from x1 until xn, or x0 xn minus 1, and so on and so forth. You can do that. We divide that into equal distance, where equal distance means that distance, we call it this as a delta x, yeah, where delta x is b minus a over n. That we split into, or we split the sub-interval into n sub-interval. Okay, and then we choose a point somewhere here, let's say xi, x star, see, x star. When we evaluate at f at x star, what we have is that we have the height of that small rectangle. So this is our fx star. Fx star. So what you can see is that if you multiply that, so we got the that part here give you a rectangle, and we can find those rectangle, of course with some error, where we multiply delta x with the height of those fxi of fx star, that give you the part of the area. Alright, to find the area for all these small subinterval, and then we sub all this thing. So the area of let's call that A, those shaded region, I would say, between A and B and X, Y0 and YFX. So that's area bounded by that region, we call it A. So we just sum up all those things. This is just approximate. We sum up I from 1 to n, f xi star, yeah, for where f xi star is any point, yeah, at I interval, times delta x. Well, delta x is that small interval. So then we take, if we take a limit, yeah, we take a limit n goes to infinity. We take a limit n goes to infinity. Those summation I 1 to n f xi star delta x. Okay, so we define this as a integral from a to b fx dx. Okay, so this summation here we call it as a Riemann sum. Right, this summation here we call it as a Riemann sum. So if you take the limit, those n goes to infinity, so that gives the definition of the definite integral. So we have we can evaluate the definite integral exactly, I would say. Okay. Now we can extend this to the double integral. So for the single integral, we obtain the area under the curve. For the double integral, so let's say we have for double integral. So what do we mean by double integral, or how does it look like? Double integral is given by this. This is, we call it double integral, a function of fxy where dy dx. So this is a double integral. So where here we integrate over some region R. So I will describe what is the region R and so on. Alright. So what we do in this case is that we just extend the concept of a single integral. Alright. So for the double integral here, we consider a function of two variables. Okay, consider a function of two variables. Consider a function of two variables. Let's say fxy, yeah. Let's say fxy. Those functions, let's say fxy. You can denote this as z if you want. Yeah, but the main point that I want to focus on the function f itself. Define on the closed region or closed rectangle. Define on a closed rectangle. Yeah, we deal with rectangle first. And this is quite easy to see. So basically our R is defined as the region or the point, all point xy, such that xy in R2, yeah, where x between A and B and y between C and D. So with this kind of a function, we look the function f as the surface. Yes, we look the function f as the surface. So you can consider in 3 dimensions x, y, and z. Okay, and then we consider the surface. Let's say this is our surface. That's a surface. So now to describe the region R, so where is the region R? So the region R is on XY plane. Yeah. So X between A and B, so this is our X on XY, on X-axis, so this is X between A and B, and Y between C and D, so this is our Y, C and D there. So this region R here, this region on XY here, this is, we call it the region R. So how does this thing look like is that if you raise that region R until it's made the surface, so you can have a kind of a volume, all right? So you have a kind of that. That's what we have. Now, to find the volume of those, to find the volume, remember that for the single integral here, we have the area. For double integral, we have the volume. That should give our volume. Now, this what we say solid here, this solid here, bounded by surface XAB, YCD. So let's call that as a S. Now the purpose now is to find the volume of S. Alright, so how to do it? Same thing with the case of single integral. So what we do is that we split the XY interval on XY AB into small sub interval, that, yeah, and as well as on Y CD, we split those things into that sub interval. Okay, so let's consider here, this is XI minus 1. Let's consider there as XI, and point, you can consider a midpoint there if you want, midpoint as a XI star. Okay, we do the same for Y. So this is, let's say YJ. Where can I write this? I can write here. Let's say this is YJ minus 1, and this point here we have here. This point here is YJ. All right, and in between, let's call this point here YJ star. Okay, so if you consider those small region bounded by XI minus 1 XI, YJ minus 1 YJ, so the region is, or the region is given by that, the small rectangle here. Yeah, and then at the middle point here is the point XI star YJ star. Okay, so if you evaluate the function, the surface with function, let's say z equal to f xy, if you evaluate that function at these particular points, so what we have, basically we have the height of the solid. This point here is given by, let's say I have that, so this point here is a, let's say z star, which is f xi star yj star. Okay, that gives you the height. So if we multiply the width and length, which is delta x and delta y, so that gives the area of those rectangle, and we multiply by the height of those cubes that give the volume. So we multiply by f xi star y j star. Okay, so this give the volume. So part of the volume, not the whole, but part of those volume. So let's call this delta V. So where delta V, this is the let's say small volume, or small a piece of, yeah, a piece of those region of solid S. So we have this. Now, in order to find the volume for the entire region S here, bounded by X between AB, Y between CD, and the surface F, what we need to do is we need to sum up all these small pieces here, add up those things, all right? We add up all those pieces for x direction. For x direction here, we add each I until, let's say, n. So I from 1 to n, and we sum up for y here, for y until m, not necessarily same n and m, yeah. J from 1 to m, those f xi star yj star delta x delta y. Okay, this will give you approximately the volume of the surface S, the volume of the, the volume of the solid S. Now we do the same here. If we take the limits, okay, where n goes to infinity, m goes to infinity, and then sum up I from 1 to n, j from 1 to m, f xi star yj star delta x delta y, yeah, you take the limit. This gives the definition of the integrate over a and b, c and d, f xy dy dx. So this gives the definition of the double integral. And this part here, we call it as a double Riemann sum. Double Riemann sum. Okay, so what we can do, if you look at again the sketch that I make here, the smaller the rectangle means if we increase number of n, we increase number of m. Alright, so this rectangle becomes smaller and smaller. The smaller the rectangle, the more accurate our solution is. Okay, I hope you can get those ideas. All right. Now we look at the what we call as iterated integral. What is iterated integral? Iterated integral. So we suppose that we have a function f of two variables x, y is continuous. You know what continuous means, yeah, in the I think you have learned a lot of continuity of a function and so on. So if a function of two variable continuous on the rectangle R A, B, C, D, yeah, this means that we have on xy plane, imagine that if we have xy and then we have z towards u, where we can have a surface, but on the plane xy itself we have that region, rectangle, yeah, x between A and B, y between C and D. So this is our R. That. Okay, so in this case, if we integrate over region R, yeah, integrate over region R, that region here, where for f xy dy dx, what we actually do is that we integrate the limit x from A to B, and y from C to D, the function f xy dy dx. Now, how to evaluate this? Of course, you can use the definition using the limit and everything, but you can for this, even for the single variable function, for function with single variable, to do or to evaluate the integral using definition is not easy. So what we can do is that we can use what we call the iterated integral. So what do we mean by iterated integral is that we integrate those double integral one by one. First, we integrate the inner parts of the integral, y C to D, f xy dy. Having done that, we integrate then over x. Okay, so of course, for the continuous function, you can write this either, you can evaluate this either with y first or x first. In this case, we consider f is continuous, smooth function. Then this is also can be written as y from C to D, x from A to B, f xy dy dx dy. Okay, in usual manner, we don't put the bracket there. So it's understood that the inner integral is to be done first. Having done the inner integral, then we evaluate the outer integral. Alright, let me give you a quick example, or one or two quick examples. Let's say we want to evaluate 0 to 3, 1 to 2, x squared y dy dx. So by looking at this integral, and as well as the limit of integration, integration here, just 0 to 3, x from 0 to 3. So if you sketch those region R here, x from 0 to 3, 0 to 3, and y from 1 to 2, y from 1 to 2. So our region is, so this is our region. Okay, so first we evaluate the inner integral, okay, by considering x is a constant first. So what we have is that, so just fix x, we don't do anything on x, but we integrate y. So what we have x squared, y squared, y from 1 to 2. So why do we need to put this y? Because to ensure that we don't, it's not confuse us between x and y. In this case, we evaluate the unit integral with respect to y, so the limit is for y. So that's why I put y equal to 1 to avoid the confusion. So having done that, we evaluate the unit integral. So we have 0 to 3, this is for x. Now this is for y, x as a fixed. So we have x squared, y, so we have 2 squared minus 1 squared dx. So what we have here is that 0 to 3, 4 minus 1 is 3, so we have 3x squared dx. That gives us, if we integrate those things, so we have x cubed over 3. Those 3 cancel out, and x from 0 to 3, that gives you 27. Okay, so you can do for the same example here. For the same example, try it yourself. Instead of integrate the inner integral with respect to y, now change the inner integral with respect to x. So outer integral is y from 1 to 2. We don't change the limit of integration. X from 0 to 3, x squared y. Now here is dx dy. In this case, we integrate with respect to x first. Having done those, then we integrate with respect to y. We should get the same answer here. So I just leave that part to you. You can do that as a simple exercise. All right. Now, did we do any mistake here? Yes, there's a mistake here. This is y squared over 2. Should be y squared over 2. Sorry about that. Y squared over 2. So this is over 2. We take out those two here, and this is 2, and then here we have 27 over 2. Okay, just a simple mistake there. Okay, let's see the second example. This is quite easy example, just to give you idea of how do we do the integration or double integral. So we integrate over the region R, x minus 3y squared dA or dr. This means if you integrate x and y, so this becomes a dx dy. So where R is the region xy such that x 0 to 2, y 1 to 2. Okay, so describe this region. Your x from 0 to 2, y from 1 to 2. So we have, this is our region, that this is x, this is y, and for f here, the function f here, you can imagine that's on the z-axis, where this z-axis here points towards yourself, points towards you, and you will have a surface there. So if you plot this in 3 dimensions, it might look like this. It might look like this, the surface. All right, the surface might be a curve, might be just a plane, or could be anything. And then we have those region x and y. So we don't have that. 0 to 2, 1 and 2, So this is our 0 to 2. Yeah, this is our region. X0 to 2. Yeah. Right? This is our arc. And this is our, so the volume is for this case we have, let's say, yeah, something like this. Yeah, so this is our volume or the solid. Yeah. Like the solid. So to evaluate those integral, we identify the limit of integration. Then those becomes, we integrate x from 0 to 2, 0 to 2 for x. Then from y, 1 to 2, y from 1 to 2. Our function is x minus 2y squared, dA now dy dx. Make sure that you have the correct combination between the limit and the variable of integral, or the dummy integral here. Okay, so if y, then the limit must be for y. If x, the limit is for x. You cannot interchange those things. Now again, we evaluate that one by one. First, consider x as a fixed or as a constant, and then we integrate with respect to y. So we have x from 0 to 2. Now we integrate with respect to y. We have xy minus 2y cubed over 3, y from 1 to 2, then dx. Okay, so that gives, integrate 0 to 2. Just substitute y, so we have xy, so 2x minus 2 over 3, 2 squared, 2 cube, cube, that, minus, this is 2, yeah, x minus 2 over 3, 1, dx. Okay, so that gives you, so what do we have here? 0 to 2, we have 2x minus x, that we have x. So this we have 27, 54, 8, 2 to 8, 16, 16 minus 16 plus 2. So we have minus 14 over 3. I think that's correct. That's x, okay, dx. Then you can proceed differentiate with respect to x. So we have 2x, x, correct. So we have x squared over 2 minus 14 over 3, x from 0 to 2. Then you can evaluate this thing. So we have 4 over 2 minus 14x, 14 over 3 times 2. Then you can evaluate this thing. Okay. One more example. Let's say we want to evaluate a region R, y sine xy dA, where our R is given as x 1 and 2, and y 0 to pi. Okay, just use the same procedure. So we have integrate, this is integrate for x from 1 to 2, x from 1 to 2, y from 0 to pi, y from 0 to pi. So y from 0 to pi. So we have y sine xy dy dx. Okay, so we have y here. You can integrate respect to y first, but what happened, I think you need to use a integration by parts. I think yes, integration by parts, or maybe substitution just u equal to xy. You can do that, or you can use, we integrate respect to x first. I think the easiest way is integrate with respect to x first. Y sine xy dx dy. Yeah, so that's what we got, is integrate from, just evaluate those things. You will have integrate y 0 to pi, then negative cos xy from 1 to 2 to the x, and then you can proceed. This gives you 0. Of course, you need some more step there. Alright. Okay. For the general case where, let's say, if your function f, if your function f can be written as, let's say, multiplication of two functions, yeah, you can split those functions. For example, g of x and h of y. Example, of course, let's say the function is like x times y. So this is a function of x, this is a function of y. You can write this, so therefore your integral over the region R, fxy dA, you can write this as a integrate, let's say, same region C to D, x from A to B, fxy dx dy. This can be written as C to D, A to D. Our f is gx hy dx dy. Then you can write this, you can split that those function y is C to D, a function y, integrate a to b, a function x dx. This is dy. Okay, you can do this if the region R is a rectangle region. And the same thing if you interchange the order of integration. Alright. Now, that's we deal with the integration of a rectangular region. What if you have more a general region? Yeah, integration of a more general region. Integration over a general region. So what we mean by general region here is that just now what we dealt with is that we deal with rectangular or rectangle, rectangle region. For the general region means we may have something like curve like that, or you may have something like this is xy, something like that. This is our region. So it's not a rectangle anymore. So in this case we have two type, of course. This we consider as a first type. This we consider as a second type. So let's look at the first type of integration, or first region. Yeah. For the type 1, where the region, let's say those region D is bounded by xy, such that x between a and b and y between two functions. We have g1x, g2x between two functions. What does this mean? So it's look like this. So let me sketch again. So we have x between a and b, y between two functions. So you have a function. For y, you might have let's say you have something like this. This is y equal to g1x, and then the other one y bounded by, let's say, that function, y equal to g2x. So our region is that. So this is our D. So our double integral, double integral becomes, we have integrate r, D in this case, D, no r anymore, D. So f xy dA, this is, we integrate. Okay, this is crucial. Okay, the choice of which one becomes inner integral and which one outer integral is crucial, because if you choose wrongly, that gives you wrong answer. So remember that for the most outer integral, you must have the limit of integration from a constant to a constant. So in this case, a constant to a constant is x. So which means we need to evaluate x for the outer integral, and then for the inner integral, you have y from g1x to g2x. F xy dy dx. So when we integrate the inner integral here, so what left is the function of fx. So next, having done those, evaluate y from g1 to g2, so that give you, let's say, from a to b, a function of x only. Then you can evaluate with respect to x. If otherwise, if you integrate with a to b first, then the limit that involve function as an outer integral, the final result that you obtain is a function, which is not correct. So let's say example. Let's say example. So let's say I want to evaluate a region D. We have x plus 2y dA, where D bounded by y equal to 2x squared and y equal to 1 plus x squared. Okay, first thing is that we need to identify the region D. You need to identify the region D. If you cannot, you fail to identify, it's difficult for you to find the limit of integration. Okay, so in order for you to identify the region of integration, I would suggest that you sketch the region. Yeah, So sketch those things. Sketch is for that function is not difficult. This is y 2x squared, so you have y equal to x squared, and then you multiply by 2. It just look like that. Okay, and the other one is y 1 plus x squared, so you have, let's say 1 is here, x squared, constant just 1, so you have a wider opening, so means you have something like that. Okay, now this is your D. Okay, and then you need to find what is x from what point to what point. Okay, so to do that, you need to, of course, you need to solve these two equations in order to find those point of intersection. Yeah, solving those things is not difficult. You have 2x squared equal to 1 plus x squared, so you have x squared minus 1 equal to 0, correct? Yeah. So you have 0x minus 1 x plus 1, so that gives you x plus minus 1, so you have minus 1 and 1. So having obtained those limits or region or interval for x, so you can evaluate those x from minus 1 to 1, y from take the smaller function. This is the smaller function, of course. So the smaller function is y equal to 2x squared to the bigger function, that one, y 1 plus x squared. The function inside is just the same, x plus 2y, now dy dx. So you can evaluate those things. Yeah, evaluate first the inner integral, that give you integrate x from minus 1 to 1, that you have we integrate respect to y, so we have xy minus 2y squared over 2 cancel out, y from 2x squared to 1 plus x squared dx. Yeah, that give you integrate x from minus 1 to 1. This is our y, so x 1 plus x squared plus 1 plus x squared squared, that's 1, minus x 2x squared, then just substitute in there, plus 2x squared squared. That's, so integrate all this thing dx. Okay, then the rest is just, you just need to evaluate those things. Yeah, integrate from x minus 1 to 1. So what you have here, what do we have here? This is x plus x cubed plus, that one is 1 plus 2x squared plus x4. That's one part. The second part here, you have 2x cubed plus 4x4 dx. Then simplify those. Minus 1 to 1. I think I rearrange those things. Take the bigger power on the left. So we have, this is x squared, this is minus 4x squared, so we have minus 3x squared, 3x quad. And then for x cubed, you have here, you have 2x cubed, minus 2x cubed. Here we have 1x cubed, so you have minus x cubed. And then we take x squared, so x squared we have 1 here, we don't have that parts, so this is plus 2x squared, and then x we have plus x, and then 1 we have plus dx. And then you can evaluate this with respect to x, that give you 32 over 15. Okay, so next we have this is the first type region, the region of the first type. Remember that we have a square or rectangle region. We have the first type region, this is that I described in this example, and then we have the second type of region. Alright, so for the second type, I think I will discuss in the next in the next video. Alright, so let me conclude what I have done this 1 hour video. I gave you from the definition of Riemann sum for the single integral. I expand those things to the double integral that we call it double sum. We take a limit that gives us the definition for the double integral. Alright, and then we deal with the integration, iterated integral over rectangle region, and then we do the integral over the general region of type 1. Alright, so with that I stop here for this lecture. Till meet you again in the next video. Thank you. Bye.